Hello, this is Tech, and since I could not actually record the lecture today, I'm going to re-record it, but this time using a my home computer. And so here we have it. Um, let's go ahead and recreate the program that we were working on this today. So let's create a new folder. We'll call this I don't know, homework. And then in here, I'm gonna create a file that resembles what we did today. This is going to be a quick summary of what we did today, so it's not going to be exactly the same. But it will still hopefully illustrate everything that we talked about earlier. So the first thing we want to do is to create a file that basically tests out all the different ways to allocate memory. So we'll just call it memory allocation. I think that's that's actually how we named the file this morning. Dot data switches into the data section, and then we can now use L1 colon to define a label. And what this is it's basically a label to remember the current location in memory, and be able to associate that location to just a symbolic name L1 in this case. Dot int basically let you allocate and initialize memory locations for 32-bit integers. So when we have something like 17, it means the expression 17 is the value that we want to represent using 32 bits. And the assembler is going to allocate 4 bytes of 32 bits per value, and so that initialize those locations to the value 17 in this case. So we have 17, and let's just say that we have 2 and 10 over here. And you can switch over to the .text section anytime you want to. You can interleave between data and text any way you want to. Basically, every time you switch the section, it will continue from the last location that was allocated before this particular section. .global underscore start to export the label underscore start. And this is the entry point of the entire program. We're not going to do much here. All we're going to do is to say move L, and instead of L1, I'm going to use L1 plus, I don't know, let's try 11. Okay, that sounds interesting, and you'll see why it is interesting. To EAX, and that will be the entire program. So we'll have the well, let me try something else too. Okay, so we're going to switch back into the data section, and this time I will use a word with I don't know, 1 2 3 4 in hexadecimal, and then byte, which allocates chunks of 8 bits instead of 16 or 32. We'll have 0x. FE is 1 byte. The character, the ASCII code of lowercase a is another byte, and then we'll have let's see, let's try something else. Let's try octal number. 067 is an octal number. And then we can now switch back into .text to continue the program. In other words, at this point, it's going to continue from the move L instruction here. And this is the actual next instruction, which is our exit code, which is move L $1 into EAX, move L $0 into EBX, and int $0x80. So here we have our program, and we're going to test out what it is going to do. Alright, so let's go ahead and save the program first. The next thing we want to do is to figure out, okay, how is memory laid out in this case. Just like what we did in class, let's go ahead and use a spreadsheet to get this done. So let me start up my spreadsheet, and then I'll resize it and put it into the window that we can see. Okay, so we'll go ahead and resize this a little bit. Unlike the full screen that we usually use in class, this is actually just a smaller window that I'm recording inside a much larger desktop. Alright, so here we have the code on one side and the spreadsheet on the other side. So we'll start with L1 plus 0, and that is the least significant byte of the 32-bit used to represent 17, the value. 17 in a base 10 as a base 10 representation is 1 1 in hexadecimal. So 0 1 1 is the least significant byte. All the other bytes of this number, they're all zeros because um, we don't need to use any more than, in this case, 5 bits to represent the value. So the first 4 bytes are like this. Okay, we have three most significant bytes for zeros, and then the least significant byte is 1 1 to represent the value of 17. And then we have 2, which is a pretty easy one because L1 plus 4, which is the least significant byte, is just going to be 02 in hexadecimal. And then once again, we have zeros for all of the other locations. I don't think the spreadsheet is smart enough to know it is 5, 6, and 7. Or maybe it does. Okay, that is pretty smart. All right, this is the third integer, which is 10 here, which is 00A, okay, in hexadecimal. And the rest would all be zeros as well. So we'll go ahead and put in all zeros here. All right. And remember what I said about the sections are all contiguous. So this means, this portion of the program is actually right next to L1 plus 11. And since it's a dot word, it's going to use up 2 bytes. And because we are using little endian, the least significant byte, which is the 3, 4, is stored as the lower position. And then the 1, 2, which is the more significant byte, is stored at a higher location. So these two locations will be L1 plus 12 and 13 respectively. And then we have the byte here, dot byte. So dot byte is going to be starting at L1 plus 14. And the first byte is just FE all by itself. The second byte is lowercase a, which is 6, 1 in hexadecimal. And then the next one is 067 as an octal number. As an octal number, 067 specifies the following bit pattern: 000 for for the most significant octal digit, 110 for the 6, and then 111 for the 7. So when you convert this into hexadecimal, we will end up with 3 because of these 2 bits here. Okay, because of these 2 bits. And then the other 4 binary digits are 0, 1, 1, 1, which will give us a 7 in hexadecimal. So 0x37 is this byte here. So now that we know what it looks like in hexadecimal, we can get rid of the binary representation. All right, so this is how I think memory should be laid out. And instead of just saying, oh, okay, this is how memory is going to be laid out and let's just use it, let's confirm that first. So we'll go ahead and exit from the editor, assemble the file, which you have to include gstabs in order to turn on the symbol table. In order to include the symbol table for debugging, -O to specify the output file, and your output file should be something .o instead of .s, and then we specify the source file. Okay, the assembling is okay. Let's do the linking. LD-O to specify mem.alloc without any extension as the executable, and then mem.alloc.o as the input file to the linker. Not a problem here. So gdb mem.alloc will debug the program. So as I said, the first thing we want to do is to display memory, and this time I want to display on a byte by byte basis, just so that we can cross-check whether the sequence we have here in the spreadsheet is the same as what we see in the debugger. So X is the command to examine, / to separate the command from the formatting. In this case, we have 17 bytes. Okay, each one is a B, which is a byte, 8-bit wide, and we want to display in hexadecimal, so that's why we have an X here. And then we also have to remember to specify the ampersand, because otherwise it refers to the value at the location of this label L1 instead of just the label L1 here. When you use the X command, you have to specify the address of where you want to start displaying, and not the variable, not using the variable itself. So that's why the ampersand is necessary. Press the enter key. Now we can cross check. So 0x 11 0 0 0 0 0 0 matches. And then we have a 02 followed by 3 zeros. Okay, that matches as well. A 0A 3 zeros, that matches. a 3 4, a 1 2, 3 4 and 1 2, FE, and then we have a 6 1, which is right here, and a 3 7 as the last one. So everything does work out. Now, if I try to display 18, I believe the last one will trigger a segmentation fault, or the debugger will complain because we actually only have 17 bytes allocated. The 18th one is not allocated. So any attempt to read past the 17th byte is going to fail. All right, so this is all working. So now the next question is try to answer this question. Okay, if we are going to use a direct operand L1 plus 11, and we're moving 4 bytes into EAX, the question is which 4 bytes are going to be copied into EAX, and also, how are these bytes going to be arranged in EAX? Because when we have 4 bytes or 32 bits, then the big question is which 8 bits are the most significant and which 8 bits are the least significant. Okay, from this map here, it is easy to identify that L1 plus 11 is here. And let me just show the code here. I can make the spreadsheet a lot smaller, so this way we can see the entire code. So L1 plus 11 is this byte, but this is only 8 bits. Now we have 16 bits, 24, and 32 bits. So that means these 4 bytes are the ones that will be copied into EAX. Now the question is, how are these bytes arranged? L1 plus 11, the one at the lowest address, is going to be the least significant byte. So this will be the rightmost 2 digits in hexadecimal. These two, being the highest at the highest location, is going to be the most significant byte. So that means the number in hexadecimal that we should see is going to be 0xFE, being the most significant 2 bytes, the most significant 2 nibbles, or base 16 digits. 1 2 3 4, and then the 0 0 should be last, because it's the least significant. So we are going to expect this number to be in EAX after line 7 executes. So let's put a breakpoint on line 7, run the program up to line 7, and well, just to make sure EAX does not have this value to begin with. So we take a look. EAX has a value of 0 before we execute line 7. Single step, take a look at EAX again, and we have in hexadecimal FE 1234000, just the way we expected it to happen. Okay, so excellent. This is just a quick review of what we talked about earlier today. So the next thing I want to do is to use the same program, but this time I will illustrate how we can use a alternative RISC version of this code to get the same thing done. So this is about the same as what we talked about in class, except I'm just using EAX and not using any other register. So what I'll do is I'm going to comment out the first line, which is the original way, the cisp way of doing things, and only use the RISC way of doing things. And if you focus on the text here, you can see that this is an immediate operand, not a direct operand anymore. In other words, I am calculating the expression, or the value of the expression L1 plus 11. L1 is an integer, but it so happens to be also the address of this particular byte, the 11 in hexadecimal. So it is really just a number. I'm adding 11 to it, so that means the end result should be here. Even though I don't know exactly the value, it doesn't really matter because it is only relative to where L1 is defined. But I am not copying this byte or any bytes around here into EAX. All I'm copying is the address itself into EAX. Okay, so that means EAX ends up to be a pointer after the first instruction to this location. The second instruction is the one that we have not really talked about a whole lot. The first operand of the second instruction, which is this part here, in parentheses we write %EAX. That's the indirect operand, which basically means we use the value of a register as an address. We go to that location, and then depending on the width of the operation, which in this case is just a L or 32 bits, then we copy 4 bytes from that location to EAX. It is okay to use the same register for both purposes. at least with the i386 architecture. So we are using EAX to drive the data bus, excuse me, to drive the address bus, um, retrieve the content at that location, or several bytes from starting with that location, and then copy those bytes into EAX. Now, because EAX is already pointing to this byte here, and this is a move long instruction, so we're going to grab this byte along with the next 3 bytes. These 4 bytes will be copied back into EAX, and it should accomplish exactly the same thing as the previous program. So what we'll do is we're going to run this. Okay, so first assemble link, and then GDB this particular program. This time we'll put a breakpoint on line 9, run the program, single step line 9, and then we'll do a IR EAX just to see what is in EAX. EAX currently has a value of 8049092. Okay, and what we also want to do is now to take a look at the label L1. So remember, you have to kind of cast it. Okay, so void pointer works, even though it's not the best way in this case, but you can do your own calculation. In other words, you can look at this number, and then you say, what is this number plus 11? Okay, you take this number, and then you add 11 to it. 11 is B, and you can do it in hexadecimal, but you can always just use print to kind of cheat and find out what is the answer. So I'm just going to copy this number and then say plus 11, and remember the 11 is in base 10, it is not in base 16. Press the enter key. We have this number here. Well, I forgot to use hexadecimal, so I will say print /x here. Alright, so we can see that this number, which is based on L1 plus 11, is exactly the same value that we have in EAX, okay, prior to the execution of line 10. So this is all good, okay. So the next instruction is going to use indirect to copy whatever EAX points to back into EAX. Now here's a trick that I did not show you in class. You can, when you use the X command, now this time we want to examine 4 bytes in hexadecimal at the location. You know what? You can use EAX here. You can actually refer to the register EAX as $EAX in GDB, and what it's going to do in this particular command is it will use the value of EAX as an address so that X knows where to examine in memory space. So you press the enter key, we have these 4 bytes. But this is displayed as 4 individual byte, which basically means the leftmost byte is the one that has the lowest address, and the one on the right hand side has the highest address. If you want to display everything as one single 32-bit thing, you can say 1, which is implicit already. You don't need the 1 if there's just one item you want to display. And then a W in GDB means 32-bit. So you press the enter key. Now it is displayed as one single 32-bit number. FE being the byte at the highest address is also the most significant byte, and that's why when you write it out as one single number, it is all the way to the left hand side. The 00 being the least significant byte because it has the lowest address according to Little Endian is also going to be on the right hand side. This is just basically the convention of writing a number that we have learned since elementary school. Okay, so now we can single step and print info register EAX again, and this time it should have this particular value. And sure enough, EAX does have this value at this point. So let me get back to the file itself. So that means this one single instruction, which is a cisp instruction, is equivalent to these 2 instructions for a RISC architecture. So I think this really kind of quickly summarized everything that we talked about today, and combined with reading some of the material that is already on the website, I think you should have enough material to start with. So go ahead and get started with your homework as early as possible. And if you have any questions about any of these items, we can talk about those when we get back to class on Tuesday. Or if you come see me during my office hour, we can definitely talk about this as well. So good luck with this particular homework assignment, and try to remember to associate these addressing modes to stuff that we have talked about already in class. Um, and that's it. All right. Good luck.